Okay, example 8, we have an object. It's being pulled up a frictionless ramp. The reason it's frictionless is because if we add the force of friction, the question becomes a lot more complicated, and we're just dealing with the basics of vectors as forces for right now. So we're moving up a frictionless ramp at an angle of 20 degrees. What is the force F which has to overcome the force of gravity? Remember, if we just left this object alone, it would slide down the ramp. Gravity would bring it down. So what is the force that we need to apply, this force F here, that we need to apply so that it will actually overcome the force of gravity? So that's what we're looking at right now. So we also have this force of gravity acting straight down. Um, and so what we're looking for is the magnitude of this F. We know that the ramp is 20 degrees, and we know that the object is 200 kilograms. So the first thing we need to find is we need to get the magnitude of the force that's being pulled straight down. How much force is gravity actually applying to us? And we need to remember that the force of gravity is actually mass in kilograms times the vector for gravity. So here we know that the mass is 200 kilograms, and for gravity we've got 9.8, and this is going to give us the magnitude of the force of gravity is 1960 newtons. So if we come back to our diagram and we look at the blue vector for force here, we can put the force of gravity anywhere we want as long as we want. Okay, so the force of gravity is one of the, it could be this long, could be this long, we're not really sure. So I'm just going to make it really, really long for right now just to see what happens. So it's going exactly straight down. And now what we see is there is another force that's exactly perpendicular to the ramp. Okay, so I'll do my best to keep this perpendicular. And eventually, so it's going about here, but eventually it actually hits, it intersects with the force of gravity. So that's what I'm going to focus on here. So I'll actually pull this gravity vector back, and now we see we have this triangle, and the nice thing about this triangle is this force, that dotted red force that we have, it's actually perpendicular to the ramp, and with right angle triangles, that's a big advantage to us because we know all about right angle triangles. So now what I'm going to do is I'm just going to recreate this triangle down below. So essentially we have a right triangle that, so recreating this triangle down below, we see that it is a right triangle, and the force of gravity straight down we already calculated. So that was, just to come back to the diagram here, that's this force here. So if you notice, that's actually the hypotenuse of this triangle. Okay, so be careful. You'll see that you see the 90-degree angle there, and you see that the force of gravity is across from it. So there's our 90-degree angle. So across from it, that's our force of gravity. Okay, so this is our 1960 here. Going back to the diagram, you'll notice that in this triangle, this right triangle that we have here in green, since we have a 90 and a 20, hopefully you can convince yourself there's a 70-degree angle up there, which means we have a 70-degree angle right there in our diagram. And what we're looking for is the magnitude of this force. So if you remember SOHCAHTOA, cos is the adjacent over the hypotenuse. So this is our adjacent over hypotenuse. So the magnitude of our force is going to be approximately 670 newtons. So we can conclude that the force needed to overcome gravity, remember that's what we were trying to figure out, is 670 newtons.